Good morning, everybody. Happy Tuesday. Hopefully everyone's doing well. If you can give me some green check marks, please, and we'll get going. Really happy to have the midterm out of the way, and very impressed with you guys' marks overall. Kind of fading into the background here. Let's just move on. That's better. There I am. Very impressed with the marks overall. Everyone did quite well, and I think with maybe one or two exceptions, everyone was kind of where I felt they should be. So hopefully you weren't terribly disappointed with your mark, but you know, everything on there looked pretty good. I had the grades up on the Thursday, and if you haven't checked them, I think it's in Unit 3, the actual assignment, but if you just go to your grades, they should all appear there. So yeah, they're all up there, Taylor. Just go to your grades page. It says midterm exam, and the marks are all up. So everyone did fairly well, which was great. How did you feel about the exam? Did you guys feel okay with it, or was it kind of like stressful, or how did you guys think it was? Was it good? Was it bad? Something you didn't expect on it? Everything you kind of thought was going to be there ended up being there? Interested to hear your guys' thoughts on it. Good. I can handle good. The Unit 4 learning guide, we weren't really, I said either today or tomorrow it would be due. So I'm going to stick with that. So if the Unit 4 learning guide, it was a long one, you can get that one in today or tomorrow. That'd be great. The kind of cutoff for the report card would be normally kind of today. I think Mrs. Wood might have put in yesterday as well. So I'm not going to include the Unit 4 learning guide on the midterm or your third term grade. So the Unit 4 learning guide, a few of you have submitted it. You know, Anna gave it to me at the midterm. So if you've submitted the Unit 4 learning guide, I'm going to take your marks, and then I will mark the Unit 4 learning guide after. So the Unit 4 will actually be part of Term 4. So Abby, I did get your message, and that's fine. So yeah, if you want to drop the learning guide off, because it would be a lot of pictures to take, that's fine. I don't have an issue with that. Just come in. I should be here, but if I'm not, or if I'm teaching or something, just slide it under my door, or just give it to somebody else and then give it to me. That's completely fine. But I would like it in the next couple of days. It won't be on this report card. It'll be on the next one. But I do want to get that marked for you guys. The other thing, well, that's good. The other grading item is, I guess the midterm will kind of be the last assignment that's on there. Now, there was a few assignments in chapters 2, Unit 2, I should say. We had a nutrient cycle, a little write-up, and then in Unit 3, we had the adapted squirrel project, and then in Unit 10, we had the plate tectonics worksheet. So some of you submitted them with the learning guides for those units. Some of you submitted them actually right into the assignment where the handout was. So I'm pretty sure I've marked them all, but if you, for some reason, have a 0 for one of those assignments, then please let me know, and I can go in and mark it if you've submitted it. So some of you might have submitted it with the learning guide, and I just didn't, put 2 and 2 together, and you might have handed it in, but I didn't mark it and put it in that other spot. So if that's the case, for Units 2, 3, or 10, the assignments that were part of those, you just want to send me a message, say, hey, Mr. Borden, I submitted the plate tectonics document with my learning guide, but I don't have a mark for it, or something like that. And that way I can go in and mark that for you. So basically, if you check your grade right now and you have everything submitted, that's going to be your Term 3 letter grade. And if you have something outstanding, then I can mark it and get it in, and we can go from there. We are going to jump into Unit 6 today. So I tried to give some of you guys the Unit 6 learning guide when we wrote the midterm. Some of you took one, some of you forgot. So anyways, we're doing Unit 6 because it is more balancing, it's more types of reactions, so really similar to what we've been doing. And Unit 5 kind of doesn't really fit in super well with it, so we'll do Unit 5 after. So I think that's it for kind of housekeeping. Does anybody have any questions about the term 3 report card, where we're at, anything like that? If not, I'll just continue on into Unit 6 here, and we'll go from there. All right. So Unit 6 is about types of reactions and how to speed up and slow down reactions. So it's only 2 sections, really short. We might be able to get through it all today, but I don't really care if it takes us the rest of the week or 2 days. But it is kind of a really quick one, and then it's done. So very similar to Unit 4 that we just finished. And one thing that I did notice that I was maybe a bit disappointed on was the last 2 pages of the midterm with the kind of written questions where you had to form your compounds. So most of you guys did a pretty good job of it, but I was kind of disappointed with the amount of people who didn't just get 100% on that stuff. So most of you did, you did fine on it, no big issues, but you're still making really small mistakes here and there. And unfortunately, those little mistakes will add up. And when you start seeing the things we're going to cover today, the stuff you learned in Unit 4 continues on into Unit 5 and 6, and we're going to, of course, do Unit 6 today. And it's really important that you have a good grasp of it. So I was trying to drill it into you guys to get you guys really good with the covalence and polyatomics and ionics and multivalence, all the different types of compounds, remembering the rules for them, how to form them, the names of them, things like that. But some of you kind of were still making little mistakes here and there. And unfortunately with the chemistry, it kind of just all adds together until you get to this Unit 6. And if you're making little mistakes along the way, when you get to this stuff, it is really going to be obvious that you're having issues. So Abby or everyone else, if you are interested in looking at your midterm exam, we can arrange that for sure. So just send me a message, and if you can come in to look at it, that'd be great. But if you absolutely can't come in, then I guess I could send, it's fine. If you want me to just scan it and send it to you, I can do that for sure. So there you go. Perfect. You too, I can do that. Anyone else that's interested, I will do that as well. If you want to come in and talk about what you got right or wrong, then I'd be happy to go through the test with you question by question, just so you're kind of aware of where you made your mistakes. All right, so I'm just going to go back real quick. I'll disappear here for a second. Types of chemical reactions is Unit 6.1, and we're going to get going on this. So basically, there's different ways we can classify chemical reactions, and depending on what we're starting with or what we're ending with, we can use the sort of different types of reactions to kind of form rules, and then we're able to predict what the reactants are, or predict what the products are going to be, just based on what you're either starting or finishing with, and then we can classify reactions based on what sort of things are there. So basically, you're going to look at a bunch of different types of reactions. You're going to be able to identify the actual type of reaction. And the reactions aren't looking any different than what we've been dealing with thus far, but we just have names for them now. So the first type of reaction is called a synthesis reaction. And a synthesis reaction takes 2 or more things and combines them together to form a compound. So basically, your reactants are going to be 2 things. A and B is just kind of placeholders here. And these 2 things are going to react to form a compound. So nothing too magical about this. And the word synthesis you might be familiar with in sort of everyday language. If something is synthesized, or if you're using a synthesizer, you're taking a bunch of inputs or a bunch of things and combining them together. So that's what's going on here. So some examples. Sodium metal and chlorine gas, if you were to combine those together, they would form sodium chloride, which is a compound. And magnesium metal reacts with oxygen gas to form magnesium oxide. So you're starting with two individual compounds, and they're forming, or two individual elements, I should say, and they're combining together to form a compound. That is a synthesis reaction. So we can give you a word equation, we can give you the symbols, and you should be able to predict what's going to happen. That's kind of the goal here. So here's a handy little chart to help you remember. This isn't in your notes, this isn't in the course, but it is right here in front of you. Just kind of wrap your brain around what's going on. So some different ways to think about what's happening here. So you take two or more things combined to form one product, or you can think of an A and a B combined together to give you AB, or you can think of this little girl in the blue dress and the little boy that's red, and they combine together to form a couple. So if that makes more sense, you go with that. Or if you like shapes, square plus circle gives you a square circle. Those are all of the different sort of analogies, I suppose, that we can use to describe a synthesis reaction. So try to remember one that works the best for you, and we'll go from there. Here's what the examples for this sort of, these types of questions are going to look like. You can end up with two things to start and then no products, and you're thinking, Mr. Borden, this is really hard. How am I going to combine these two things together? I don't know anything about what's going to happen. But the idea here is that you should be able to see the reactants and be able to predict what the products are going to be. So if you are starting out with two individual elements, in this case magnesium and nitrogen, you're going to know that those are combining together to give you a compound, to give you a synthesis type reaction. So what I'm going to do is I'm going to jump over to my notepad here, and we're going to do the first examples here. Now, in order to get this kind of done in a timely manner, I probably won't balance all of these. More interested in what products you're going to form, so know that these are unbalanced. If we have tons of time left at the end, we can go back and balance them all, but that's going to be just a lot of work. So more interested in figuring out what the products are going to be. So we're looking here. These are synthesis. And the examples I don't believe are in your notes. So if you had a separate sheet of paper, you could just copy these down and kind of add it to the notes. So what we need to do is kind of figure out how these things are going to combine together. So we have magnesium and nitrogen are going to combine together to give us a compound. But we don't know what that compound is going to be. But we do know the rules for forming compounds. We know magnesium is Mg, and magnesium always has a charge of +2. Nitrogen is N, and nitrogen always has a charge of -3. So if I'm going to form a compound with these two elements, I'm going to have to balance them out properly in terms of charge, and I'm going to end up with Mg, 3, and 2, if you think about crisscrossing your charges down. So that is what we're going to end up with here. How do I know it's going to end up that way? Well, if you think, what else could happen? What other combinations of magnesium and nitrogen are there? When we write a compound, the metal's always first, the non-metal's second. These can only combine one way. They're two individual elements. What else could we do? Well, there's really no other choices. It's not like one is going to disappear. We know the law of conservation of mass says if we start with magnesium and nitrogen, we need to finish with magnesium and nitrogen. So there's really nothing other, there's no other possible outcomes that could happen here. It's just, that's it. That's just what you end with. We do not need to balance these. These are going to just remain unbalanced. But for the most part, we would end up balancing them, but just for the sake of time today, I don't want to spend a ton of time going through all these things and balancing them. So these two are the synthesis examples here, so we'll jump down to the next one, the aluminum and the fluorine. So again, same idea. I have aluminum by itself. I'm going to add to it fluorine. And what am I going to get? Well, aluminum is Al, always has a charge of +3, never changes. And then fluorine is F, always has a charge of -1. So how are these things going to combine together? Well, there's only one possible way that can happen. The fluorine's not going to come first because it's a nonmetal, so it always has to come second. The aluminum's the metal, so it goes first. So crisscrossing my charges, if you want to think of it in terms of crisscrossing, that's fine. Aluminum has a charge of +3 and fluorine's -1, so I'm going to need 3 fluorines to balance out that reaction in terms of making that compound. So typically we'd go through and balance this. We can write our little lines in front of all these things, but again, we're not going to today. So that's what that is going to do in terms of a product. So the first type of reaction, synthesis, if you start with 2 individual elements, you're going to end up with those forming a compound. All right. The second type of reaction that you need to know is a decomposition reaction. Now, just like we talked about in biology, if something is decomposing or a decomposer, detrivores, they're breaking things down. So we can use the meaning of the word decompose and know that a decomposition reaction is taking something, a compound, and breaking it apart. It's just that simple. So if we started out with just general, the A's and B's are just any element, 2 elements together, A and B, and you break them apart, you end up with a decomposition reaction. So we start with AB, we end with A and B, where A and B are just elements. We can do this with table salt. Sodium chloride breaks apart to give us, sodium and chlorine. There we go. Another example, H2O. We can take water, we can add some electricity to it, we can break it into hydrogen and oxygen gas. So the easy way to identify a decomposition reaction is you're starting with one thing. There'll be no plus signs on your reactants side. All right, so analogy time. One reactant breaks apart to form 2 products. So we have A and B breaks up into A and B. Or we have NaCl breaks up into Na and Cl. Or we have a couple and they break up. And you can do it with shapes. You have a square and a circle, arrow, circle and square. Just that straightforward. So let's look at a couple examples of this. Again, really easy to see that this is going to be a decomposition reaction because you're only starting with one reactant. Notice there's no plus signs here. Again, we're supposed to predict what's going to happen based on the type of reaction. So if you start with one thing, the only possible thing that could happen is it breaks apart. So there you go. This was the same as the elephant's toothpaste reaction that I did in class a couple days ago, or last day I suppose, where we took hydrogen peroxide, which is H2O2, and we broke it into water and oxygen gas. That's a decomposition type reaction. So we only started with one thing and ended up with 2. So let's try to predict what's going to happen. We have Au and Cl. So what's going to happen here? Well, I'm going to break it apart. Au. And then Cl. Now, this is where it becomes really important to remember, I call them the magic 7 or the diatomic 7. Now chlorine, Cl, when it exists by itself, never exists as just Cl. When it's by itself, it's diatomic. So it's really, 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 really important that you have a Cl with a little 2 next to it. So the 2 becomes very important. because chlorine's one of the diatomic 7 or the magic 7 or whatever you want to think of them as, if it exists by itself, it needs to have a 2 next to it. If you forget the 2, you imagine trying to balance this thing, you're going to not balance it correctly. So it's just one of these additional things that you need to do. The next one, K2O. What's going to happen? Well, potassium oxide is going to break apart into potassium, and then I separate my elements, and then oxygen. And again, oxygen is one of the magic 7, the diatomic 7. So when it is by itself, it needs a 2. Why did I not put a 2 next to the potassium? Well, potassium isn't one of the 7. Same thing up above when I did AU or gold. Gold wasn't one of the diatomic 7. So when it's by itself, it's just potassium. It's fine. But if it's one of the 7 and it's by itself, you need to have the 2 next to it. It needs to be diatomic. These were examples of decomposition reactions. All right, so synthesis, 2 individual elements form together to give a compound. Decomposition is the opposite. You start with one thing, they break down into 2 individual elements. Taylor, if you look at the notes from section, what would it be, 4.3, I guess, the very last slide when we were doing word equations, we talked about the diatomic 7, or I call them the magic 7. So 7 elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. When they're by themselves, they always exist with a 2 next to them. Those are the magic 7. So that was from your notes from last class. All right. Sorry, today's class is a bit dry, not a lot happening, just types of reactions. Single replacement. It's kind of what it sounds like. Single replacement. You're replacing something with something that's single. So if you have something by itself, in this case we're using the letter A, just kind of hanging out by itself, and then you have a compound, BC. What's going to happen is the A is going to replace the B in the compound. So it's going to kick the B out and form a compound. So it can happen that the element that's by itself is sometimes a metal, or it can happen that the element by itself is sometimes a non-metal. It doesn't matter. It just basically is the same process. But whatever is by itself is replacing something in the compound. So the way to identify a single replacement type reaction is you're going to have an element and a compound to begin. So your reactants are going to be a compound and an element. Then the element's going to kick one of the things out of the compound. So you can see here the aluminum is going to kick the copper out, and you're going to end up with copper by itself and then aluminum chloride. And same down below here, the fluorine is going to kick the iodine out, and you get iodine by itself and then NaF. Sometimes students have a difficult time trying to wrap their head around this one because there are some possibilities to deal with. So we'll look at the analogies and then we will discuss a couple examples and see how you guys do. So just in general, you have a compound A and B, and then you have an individual element C. It doesn't matter what order these things come in. The C can be in front of the AB, or the AB can come first. But what's happening is the C is going to replace the B, so the B is going to be by itself, and then you have AC. So some more examples, and there you have it. I want you guys to try these 2 examples. So see if you can figure out what's going to happen here. I suppose we do have a couple choices to make, a couple decisions to make. In terms of the aluminum, what is the aluminum going to replace in the first example here? Is the aluminum going to replace the PB, the lead, or is the aluminum going to replace the chlorine? And Taylor, this is kind of getting to your question here. How do we know what it's going to replace? Do we know? Does it always kick out the second element? We got to kind of think in terms of what we know about compounds thus far. I'm going to jump over to my little notepad here. So we're looking at these ones right here. These are our single replacement reactions. Does it replace a metal if it's a metal? And non-metal if it's a non-metal? That makes sense. Can we think of maybe something that would come of that, Avery? Let's take, for example, the first one we're doing here. What if the aluminum tried to kick out the chlorine? So we had PbAl. Can anyone see a problem with PbAl? There is a problem here. What kind of rule does this compound, PbAl, violate? Why is it wrong? Why does the aluminum not replace the chlorine? Can anyone think of what could be possibly wrong there? Two metals. You got it, Taylor. And Ava. And Abby. Yeah, so we have two metals together. Can we ever have two metals that form a compound? No, we can't do that. You can't have two metals forming a compound. It just doesn't work that way. So that possibility doesn't work. Are there any other possibilities? Yeah, there's only one other thing that could happen. So let's do that. Now, one thing that you did, Taylor, when you wrote down PbAl plus Cl4 is you were thinking, well, I had 4 chlorines on one side, so I'm going to end up with 4 chlorines on the other, which is kind of correct, but we need to balance to figure out if that 4 is going to go there or not. And when we balance, the number goes in front. So we're not balancing today yet. So it's important that when we form the compounds or when something's by itself, we don't put anything behind it that we don't really mean. Yeah, Abby, that's a great question. Are we going to end up with covalent type compounds? Generally speaking, no, not in Science 10. I don't want to say never, it may happen, but generally speaking, when you're doing a single replacement reaction, you're going to be dealing with ionic type compounds, unless they give you something that is, they wouldn't though. No, they'll 99.9% of the time be ionic compounds. I'm trying to think of, with covalent, it would be really hard for you to predict because you could end up with CO, CO2, CO3. You don't know what ratios to use in terms of the covalent compounds, so I'm thinking we probably won't encounter them with without ionic compounds. So we've decided that the aluminum is going to replace the lead, because those are metals. Metal replaces metal, non-metal replaces non-metal. All right, so I need to kind of think in terms of my new compound here. Aluminum I know is always +3, and chlorine is always -1. So when I form a compound with aluminum and chlorine, I'm going to end up with AlCl3. And then what happens to the lead, the Pb? Well, it just kind of hangs out by itself. Do I need to indicate a charge or anything here? No, I don't. It's not important. I'm not writing down ions. I'm dealing with compounds and elements. So I don't need to write down any charges. I don't need to write down anything else. I'm just happy to leave it like this. And for whatever reasons, sometimes students really struggle with the idea of lead being by itself and just being Pb. That's it. It's just lead. Just like aluminum here was just Al. There's nothing special about it. If I just had some aluminum foil like I had last class, tin foil, what is it? It's just aluminum. It's not Al2. It's not aluminum combined with anything else. It's just Al. That's it. So that's all there is to it. All right, next example. What's going to happen here? We're looking down below here. That's not perfectly clear. Trying to fit everything on one page. Na plus Cu2O, what does that produce? Taylor, that's right. Yeah, we're going to end up with always a non-metal and a metal together. You don't want two metals together. That's not going to work. And you don't want two non-metals together. Because in almost all of these examples, there's going to be ionic compounds. So metal, non-metal. So you're right there. So this example here, Na plus Cu2O, we have, again, a metal, Na. And the metal is going to replace the metal. So we're going to end up with Na. Kicking Cu out. So we know we're going to end up with just copper by itself. And again, it's not Cu with a 2 next to it. I know a lot of us are going to be tempted to write Cu with a 2 there because you had a 2 here, but it's just copper. It's copper by itself. It's not Cu2. The reason it was a 2 to begin with was because it was combined with oxygen. But now it's just by itself. If you're just by yourself and you're not one of the diatomic 7, hydrogen and nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, then you just exist by yourself as just Na or just Cu or just Al. So the Cu gets booted out. It's by itself now. That's okay. It doesn't mind being by itself. And then we need to look at forming a compound with Na and the O. So sodium is always Na, always plus 1, and oxygen is always O, and it's always minus 2. So if I were to crisscross my charges, I would end up with Na, 2O. Shouldn't copper be at the back? It doesn't matter. It's kind of like a math question. If I wrote like 7 plus 3 is 10, or 3 plus 7 is still 10. Or I could write something like 7 plus 3 is equal to 4 plus 6, or 7 plus 3 is equal to 6 plus 4. It doesn't matter the order. Just like math, same in chemistry, the order just doesn't really matter. So there you have it. When you form the compound, when you're predicting, and you need to take into consideration the ion charges. You could always put it at the back to keep it the same if that's what makes sense to you or what you can kind of visualize happening, for sure. That's a great way to think about it. But in terms of kind of the logistics of everything, it doesn't need to be at the back. There's no requirement for it to be at the back. All right, so those are single replacement reactions. Our next one is going to be a double replacement reaction. Just make sure I haven't skipped anything here. So we just did those two examples, perfect. Double replacement reaction. In a single replacement reaction, you had something that was single and it kicked out something in the other equation, and you ended up with something by itself and a compound being produced. In a double replacement reaction, you are going to have two compounds, compound 1, compound 2, and what's going to happen is they're going to switch partners. And you're going to end up with two separate compounds to finish. So it looks really similar to a single replacement reaction, but in this case, it is called a double replacement reaction. So the partners are switching. So you can see the example here is really complicated looking, but we have K and CrO4, and we have another compound, Ag and NO3. And what's going to happen is the potassium, or the K, is going to switch with the Ag, or the silver. So you're going to end up with K and NO3 and Ag and CrO4. So possibly not the best example to start with, but you can maybe get an idea of what's going on here. So A and B plus D and C, again, we don't want to end up with metal, metal, and non-metal, non-metal. So the metals are going to switch. That's kind of the easy way to think about it. And the non-metals just maybe kind of stay where they are. Or if you want to think about the non-metals switching, that's fine as well. So another example without polyatomics, Mg and Cl and Be and F, and the metals are going to switch. So the Mg is going to hang out with the F, and the Be is going to hang out with the Cl. Kind of see how that happens. Another analogy, partner swap here. You have the blue girl and the red boy, and then the blue girl is going to switch with the green girl. Or you can think about it in terms of shapes. Whatever way works best for you to wrap your head around this, that's the way you want to think about it. So we're going to start with two compounds. We're going to end with two compounds. All right, let's look at two examples of this. Now, if you've kind of been with me so far, you probably have a pretty good idea of how this is going to kind of work. I will warn you, you don't want to end up putting two metals together or two non-metals together. So what I want to do is I want to just give you a second to kind of go through this. If you want to ask a question in chat to kind of straighten it out in your brain, that's fine. But I would like you to kind of try this on your own. This is maybe a little bit more difficult than the first few we've done, but I think you guys are capable of this stuff. So your metal is going to replace your metals are going to switch. Partner is going to stay there. See if you can do the first one, CaS and NaOH. What are you going to end up with there? If anyone wants to throw one compound into chat maybe, and see if others agree or disagree with you, that would probably be a good start. Does anyone want to predict what's going to happen here? Since there's three, any of them polyatomic or no? That's a really great observation. There is definitely a polyatomic happening here. So the OH, the hydroxide, the NaOH, is going to be your polyatomic. So the Ca and the Na are going to switch. That's right. The OH, that polyatomic group, is going to stay together as a polyatomic group. Maybe that's where we were getting kind of caught up. So what's going to happen is the Ca here and the Na are going to switch partners. So the Ca is going to bond with the OH, and the Na is going to bond with the S. We're going to always end up with two compounds if we start with two. So you're going to end up with two things here. So calcium, Ca, always has a charge of +2, always. And the Ca was bonded with the S, but now it's going to switch partners. Because we don't want to end up with Ca and Na. That's calcium and sodium together. That's two metals, not going to work. So we don't want that to happen. So the Ca and the Na are going to switch partners. So the Ca is always +2. The OH, it's a group, it's polyatomic, page 5 of your data booklet. It's OH, it's hydroxide. That group always has a charge of -1, that never changes. So it's the Ca is +2, the OH is -1. So we can form a compound with this. There's only one way these elements will combine, and that is CaOH, and then we need to put a bracket and a 2, because we need two groups of that OH to combine with the one Ca for the charges to balance out. So that's our first compound. The second one we have here is Na and S. There's only one way sodium and sulfur can combine, and that is going to be Na with a 2, because we had the 2 here. So we need two sodiums to balance out with one sulfur. So if you think about crisscrossing, that works. If you think about just the charges balancing out, that'll work as well. So that is what you are going to end up with. CaOH2 and Na2S. All right, this next one, again, a little bit tricky, but now that you've seen one example, just going down here, I will tell you that this PO4 group of this phosphate is a polyatomic ion, so that group is going to stick together. How about you try this one again? And if you want to throw a compound into chat, just kind of make sure you're on the right track. Do that. But you don't want to end up with two metals together, and you don't want to end up with two non-metals, so a polyatomic and a non-metal together. It's not going to work. I'm thinking you guys are going to just do this one for me. You're going to have to put in the answers. I'm just going to relax. Sit here. You guys can tell me how it's done. Anyone brave out there today? It'd be really great to hear from someone we don't normally hear from. And if you're wrong, I promise I'm not going to make fun of you or anything. This is just getting started, just learning how to do these things. It's okay to make mistakes. I make mistakes all the time. Now, I've been doing this for a long time. What are we thinking? See, Ava, you don't have to worry about the 2s and 3s being subscripts. If you can just get in a chat and we can see it, that'd be good. All right, let's see what we have here. Ava says Ki and Mg3PO42 with some brackets. Ava and Abby are going to agree. Does anybody disagree with that? Or are we all in agreement with what that looks like? Give you a chance to disagree. Anna agrees. We have everyone with a name that begins with A in agreement. Excellent. I know, it's kind of fun if somebody, says, no, I disagree. Taylor agrees as well. Well, if everyone agrees, well, not everyone, the vocal minority agree, then I guess we have to agree too. There we go. All right, let's see what we can do here. So we've decided that the K and the I are going to combine together. Or you're thinking about the potassium and the magnesium switching places. That's essentially what's going to happen here. And we know we can only form these compounds one way. So this is where students will make mistakes. They'll write K3, I2. Well, why is that wrong? I started with K3 here and I started with I2 here. Why do I not want to write that? What is kind of the issue with that? Is there an issue with that? Is there anything wrong with that? I've swapped the K and the Mg, so now I have K and I. Where's the problem? It doesn't balance the charges. That's right. So remember, when we're doing these types of problems, the potassium and the iodine, the K and the I, they can only go together one way. Even though we started with 3 Ks and 2 Is, we can't just say, okay, 3 Ks, 2 Is and be done. We need to be able to form the compound properly. And then the next step, which we aren't doing today, just so we can get all of this stuff done, is we'd have to then balance. So that's why we balance, to make sure that the compounds, everything kind of works out. So I don't want to end up with that. What I want to do is I want to say, okay, I have potassium, that's K, and potassium always has a charge of +1. And iodine is I, and iodine always has a charge of -1. So if I were to balance those charges, I would end up with K and I. They're 1 and 1. they balance each other out. All right, I have another compound, so I want to separate it with a plus sign. And now I'm going to have magnesium, which is Mg. Magnesium always has a charge +2. And then this PO4 group. So PO4, I don't remember that one, so I'm going to go to my polyatomic ion sheet. PO4 is phosphate, always has a charge of -3. No exceptions. They're not multivalent. That's the only way they can combine. And I don't know if we're going to run into anything multivalent, so I might as well say it. If you have a multivalent, let's say we had like copper, which was +1 on the reactant side, copper will continue to be +1 on the product side. I know this example doesn't have that sort of trick in it, but if you have a multivalent metal, something that has more than one charge, if it's +2 on one side, it'll remain +2 on the other side. That's not happening here, so we don't need to worry about it, but I'm sure you will encounter it at some point. All right, I need to balance this out. So I have Mg, I need to bring the 3 down, and then I have PO4, and I need to bring the 2 down, or 2 groups of that. Now, if I had the time, I would balance this. I would say, okay, I have 1 potassium on the product side, I have 3 potassiums on the reactant side. I'd start to balance, go from there. But we're not balancing right now just because, unfortunately, we don't have all kinds of time. So that's what it's going to look like. And I believe Ava was correct and everyone agreed with her. So you guys are smart. Good job. All right, we only have a couple left. I know it's kind of tedious and a little slow today, but unfortunately, we need to get through it. So there you go. Neutralization is a bit of a tricky one because we haven't talked about acids or bases yet. But in Unit 5, which I skipped because the only sort of reference to Unit 5 from Unit 6 is this one little piece here, is that acids always begin with the letter H. They always begin with a hydrogen, and bases always end in OH. That's the definition of an acid. It starts with an H, a base, by definition, ends in an OH. So when you have an acid and a base and you combine them together, what happens is the acid and the base neutralize each other, and you end up with salt and water. Now, so far, your encounters with salt is just table salt. That's all you know as being a salt. But salt is actually a broad category of compounds. And when you have a metal and a non-metal combined together, generally speaking, they form a salt. There's a few exceptions. Things with oxygen sometimes don't form salts, things of that nature. But generally speaking, if you have a metal and non-metal, you stick them together, you're going to form a salt. So the salt you have in your house is sodium chloride, NaCl. That's what you put on your food. Sodium chloride is just one type of salt. It's table salt everyone's kind of familiar with. But if you took a metal and a non-metal, you combine them together, they actually form what's called a salt. So a salt you think is just one thing, but it's actually a broad category of things. So sulfuric acid's used to neutralize calcium hydroxide. This all sounds quite complicated, but I assure you, you've dealt with all of these things before, maybe not sulfuric acid. H2SO4 is sulfuric acid, CaOH. So it starts with an H, that means it's an acid. It ends with an OH, you get a base. So we have an acid and a base. Together give us CaSO4 and H2O. We're going to look at where the H2O comes from here in a second, but what I can tell you is that this neutralization reaction is just a special type of double replacement reaction. It's almost completely identical. It is in fact completely identical to the previous examples we did, except it's just special because you have an acid and a base. So there's 2 examples here. Before we get to those, let's look at this. This is just a little sheet of notes. This is not in your notes. It's just my sort of supplement to your notes. Because we haven't done Unit 5, it's important to know what's going on here. So We're going to talk a bunch about this in Unit 5, but for now, if you start with an H, you are an acid. So HCl is hydrochloric acid, HBr, hydrobromic acid, HF, hydrofluoric acid. These are all examples of acids, and they can have polyatomics tagged onto the end. So we saw H2SO4, sulfuric acid, and bases. Bases always end in OH. So if anything, NaOH, sodium hydroxide, calcium hydroxide, strontium hydroxide, all of these things end in OH, they're bases. And then salts are kind of, by definition, what happens when you react an acid and a base together. So if you end up with NaCl, that's a salt. CuCl2, that's a salt. Z, R, and F, zinc-chromium fluoride, those are salt. So these salts are this kind of broad category of elements that you get when you react a base and an acid together. So that being said, let's look at our analogies, and then we'll look at a couple examples. So I said, we'd get to where the water comes from, and this is where the water comes from. It's a double replacement reaction. So your metals are going to kind of switch. The trick here, not a trick, but the H is acting like a metal in your acid. So your H is kind of like a metal, and it's going to swap with the B. So you're going to end up with H and OH. HOH. What is that? Well, that's just a really funny way of writing water. HOH. It's H2O. You have two H's and an O. So it's really just a double replacement reaction. You have the B and the A are going to end up together, and that's your salt. So there's your analogies. Again, double replacement, same thing, just a little bit of a special one because you end up with this HOH. Let's look at a couple examples. If you really, I'll do one and then you guys can do the next one by yourselves because it's really, looks kind of messy. It's not terribly difficult. All right, so here we are. These are our neutralizations. Neutralization type reactions. HBr, NaOH. All right, so we've decided that the H and the Na are going to switch partners. So I'm going to end up with HOH, which is just a funny way of writing H2O. You can think of it as H and an OH. That's exactly right, Abby. There's no, if you're doing it, you see two compounds to start, it's a double replacement. The only sort of catch to your logic here is that if you're asked to identify the type of reaction, it's important to know that this is a special type of double replacement. So you're looking at a neutralization reaction. So although a neutralization reaction is technically a double replacement reaction, it's a special type. So you would be able to predict the products correctly for sure. But if it asked you to identify it and you said it was double replacement, we're looking for a little bit more specific. So a neutralization is a special type of double replacement reaction. So you end up with this HOH, that's just water, and then what's left is your Na and your Br. So you're going to combine together your Na and Br. And by definition, if you have an acid and a base react or neutralize one another, you're going to end up with a water and a salt. Sodium's always +1, bromine's always -1. NaBr is going to balance out. We end up with NaBr. I guess the important thing here is to remember to put your metal first. You don't want to end up with BrNa. That's not good. So you don't want to run that risk. But there you go. Special type of double replacement, which we call a neutralization. As soon as we see an H to begin and an OH to end, we know we have an acid-base neutralization. See what you can do with this one, the second one down at the bottom here. And we only have one type left, which is kind of nice. So see if you can figure out what type of salt you're going to have, and then what's going to happen with the H and the OH. Let's give you a second to do that. If you're feeling brave, you want to throw it into chat. Haven't really spoken up yet. This would be a great opportunity to check your compound forming skills. All right. This is a bit of a trickier one. I mean, it's not terribly difficult, but it isn't super straightforward. So hopefully you've just attempted it. See what you ended up with. So if we take the H and the OH and we put it together, and again, you don't want to get caught up with the H had a 3 next to it on my reactant side, and the OH, there's 2 groups of that on my reactant side. So how many waters am I going to end up with? That's a problem we're going to deal with when we balance it later. So don't get caught up in the H3, OH2 sort of thing as the reactants. You don't want to get thrown off by that. It's important to recognize that you're combining H and OH together. That's going to give you water. So we have H2O. And then we have the Mg and the PO4, magnesium. Yep, we started with 1, but it doesn't matter. Magnesium is always +2. PO4 group is always -3. So I'm going to separate these with a plus sign. And I'm going to end up with Mg3PO4. And because I have more than one of that group, I have 2 of the group, I put it in brackets so I don't get confused and write PO42. And Anna, you were on the money here, H2O, Mg3PO4, 2. So that's terrific, because that's a bit of a trickier one. That's kind of as messy as they'll get, that one right there. The last type we're going to look at is a combustion reaction. And combustion reactions are gifts. You know how I said, oh, you get to a covalent type question? It's kind of a gift. That's what's going to happen with your combustion reactions, because they're really obvious. And predicting the products is always the same. So when you guys see a combustion reaction, you're going to be really thankful, because they're really, really easy to deal with. Hard to balance, easy to deal with in terms of the type of reaction. So a combustion reaction is the last type we're going to deal with. And combustion reactions occur when you have a compound or an element and it reacts with oxygen gas. So for the purposes of this course, combustion reaction will always have a hydrocarbon, hydrogen, carbon, hydrocarbon. So hydrogen and carbon in some combination reacts with oxygen gas. The beauty of a combustion reaction is the products are always the same. Doesn't matter which hydrocarbon you burn, if it's gasoline, candle wax, anything. Doesn't matter what you're burning, you're always going to produce carbon dioxide and water. So you can talk about burning methane, CH4, swamp gas, methane, natural gas, and combining with oxygen, So CH4 and O2 produces carbon dioxide and water. That's it. Acetylene is a type of hydrocarbon. It has ethane in it, and C2H2 is acetylene. Doesn't have ethane in it. Sorry, C2H6. So acetylene, C2H2, plus oxygen gas gives you carbon dioxide and water. Carbohydrates like glucose, C6H12O6 plus O2 produces carbon dioxide and water. So we always end up with the same products. It's a specific type of double replacement. It doesn't really work out if you're switching partners because these ones are bonded covalently. So you're going to end up with a hydrocarbon to start with and oxygen gas. So there are going to be no other, I shouldn't say that. If you see oxygen gas, it's probably going to be a combustion. It might be a single replacement type reaction. But if it has a hydrocarbon and oxygen, then you know it's going to be a combustion type reaction. So not another type of double replacement because these are all covalently bonded. You're going to have C something, so the X is just replacing a number, and H something. If you have a hydrocarbon, C and H, and oxygen gas, you know you're going to produce carbon dioxide and water. Specific example, CH4, methane gas, plus oxygen, produces carbon dioxide and water. So let's look at a couple examples. These are going to look like this. C4H10 plus O2, what is that going to produce? C3H8 plus O2, what is that going to produce? Now, I said these are gifts, and they really are when you get these on your tests, because you're always going to end up with CO2 and H2O. CO2 and H2O. That's it. Just CO2 and H2O. It doesn't really matter what you're starting with. You're going to end up with CO2 and H2O as your product. All the time. I could make up some hydrocarbon. It probably won't be a stable one, but I could have like C36H, I don't even know, 80 something plus O2. What happens? Well, I'm going to end up with CO2 and H2O all the time. That's not a stable hydrocarbon, so ignore that. But that's what it's going to end up like. Always going to have the same products, carbon dioxide and water. Anytime you burn a hydrocarbon, you're going to end up with carbon dioxide and water being produced. That's it. So what I want to do is probably just take a little break here. Maybe we'll look at some examples from the learning guide after the break. And then I think I want to talk about reaction rates because we might as well just get all of chapter 6 or unit 6 done all in one day. I'm pretty sure that's it for slides. Yep, that's it for the notes. So before we go for break, does anybody have any questions about types of reactions? We'll look at a few more examples, but they're all there. So you have a synthesis reaction where you start with two individual compounds, they combine together, decomposition, one thing breaks down, single replacement, double replacement, and then the two special ones, neutralization and combustion. Nobody had any questions, which is good. It means I've done an excellent job of describing all of these things for you, or you're so lost you don't even know where to begin. Let's hope it was an excellent job. It is about 10 after 10. Let's maybe take, very small unit, Anna. Let's maybe take 10 minutes, and I'll meet you guys back here in 10. So grab a drink, grab a snack, get up, move around a little bit, get the blood flowing, and we'll see you guys in 10 minutes. Thanks. Hi guys, welcome back. If you can give me a green check mark and let me know you're with me, and then we will carry on. So I just want to take a look at the learning guide first, and then we might get through the second section, which is really quick. I just want to see if this loaded. It did. Fantastic. Thanks, guys. All right, so we've gone through the types of chemical reactions. They're single replacement, double replacement, synthesis, decomposition, and then neutralization and combustion. So those are your six choices. For the learning guide, the part that you're going to fill in, Unit 6.1, basically it has some just, brief sort of summaries of all the different types. And then there is a bunch of classify the following reactions as synthesis, decomposition, double replacement, single replacement, neutralization, or combustion. And then it says, if you want extra balancing practice, then also balance the reactions. I want you guys to have extra balancing practice. So for number 2 on your learning guide, I'm not even going to guess as to what page it is after the kerfuffle we had last time. I want you guys to balance. And what that means is that you will have to do the work on a separate piece of paper, unless you can write really, really small and you can fit H and O in here and H and O and then balance. It's going to get a bit trickier with some of the bigger ones. But if you feel you have enough room there, good. If you don't have enough room, do it on a separate sheet of paper and include that when you submit it. For the first part, like including the descriptions here for question 1 out of 6.1, is that what you're talking about, Abby? I'm not concerned if the examples you use here are not balanced. That's fine. Don't worry about balancing question 1. So don't balance question 1, but question 2, when it asks you to identify the type, and then it gives you little blanks to balance it, please balance those. So I'm talking question 2 here, balance them. If you can fit them in, awesome. If you want extra room, do it on a separate sheet of paper, staple that onto the back, submit it. That would be great. Maybe let's do a couple of these and then we'll move on to the last section, which won't take terribly long. I'll let you guys balance them, but for now I just want to talk about the types of reactions. So with practice, you'll get to understand and you get to see that things happen again and again and again. That's why we classify things. All country music sounds relatively the same. Why? Well, it has the same sort of ingredients each time. Rap music, same ingredients. Pop music, same ingredients. We've classified music. Now we're classifying reactions based on kind of what's going on in them. So as soon as I see like 2A, I see that there's only one reactant. There's only one thing to start with. So if you only have one reactant, what options do we have in terms of identifying the types of reactions here? You don't really have a lot of choice. I believe in your notes, I'm just going to scroll up. No, we didn't include the little summary chart. All right. In the course, I might as well just go find it right now while we're here. In the course notes that kind of go along with your fill in the blank notes, there is a little summary chart that I want to look at. Use my mouse here, scroll down. So we did types of chemical reactions. And give this a second to load. Summary of reactions is down here. Give that a second to load. Basically, it's a chart that has, maybe it's not in here. Why did I think it was in here? Excellent review of the types of reactions. No, no, no. All right. Maybe it's at the top. Anyways, there's a chart. I'll find it. I'll include it in the course so you guys can have it. That has a summary of all the different types of reactions all in one spot. I'm sure it's somewhere in here, but I'll find it and have it for you next day so you guys can have it. And basically it just has all of the sort of the descriptions that we've gone through thus far all in one spot. So if you're starting with one reactant, only one, what type of reaction must this be? Does anyone want to throw it into chat? And using the abbreviations like you're doing there that's fine by me. We don't need to be too terribly fancy when we're doing this sort of thing. So DEC, that's great. That'll work. It's at the bottom of the last question for 2. Anyways, I'll find it. And it's there somewhere. Decomposition is right. You can only start with one thing if you are doing a decomposition reaction. That's what's happening here. And H2O2 is actually hydrogen peroxide. This is the example that we did in class. The next one is kind of obvious, but it's not until you've gotten lots and lots of practice at it. But it starts with 2 compounds. So if you're starting with 2 compounds, you're either going to be a double replacement, you're going to be a neutralization, or you're going to be a combustion. So in this case, I see that I have an H to begin with and an OH to end here. So this is a special type of double replacement. So I don't want to write double replacement. I'm going to write neutralization because I'm starting with an acid and a base. How about this next one? Letter C. What do we think? Anyone want to take a shot at that one? You have aluminum and you have nickel bromide. What's going to happen here? What are our choices? So really we're starting with a single element and a compound. So we've got single replacement and we've got a vote for double replacement. Does anybody else want to support one of the others? Do we have a tiebreaker? Or we can think about what's going on here. Can we start do we have the right ingredients sort of thing for a single replacement, or do we have the right ingredients for a double replacement? So for a single replacement, we're going to have A and something like a compound. Is that what we have here? We have an element by itself and a compound. The aluminum looks like it's kicking the nickel out. Now the nickel's by itself, and then we have the aluminum and the bromine. So this is a single replacement because the aluminum kicked the nickel out. So that's why that's a single replacement. Let's do letter D, and then I'll leave the rest for you guys to do later on. Letter D, we have nitrogen and hydrogen. These are 2 diatomic elements when they exist by themselves, N2 and H2. And then those are combining together to give us NH3. So we have 2 individual elements combining to give us a compound. Anytime we end with one thing, we know we've had a synthesis reaction. We're synthesizing 2 elements together to give us a compound. So that is the types of compounds. I want you to balance those, so you'll have to go back and do the first 4. I want you to, more importantly, be able to identify each one of those reaction types. So I'll give you guys that to do for homework. And what I would love to do is jump into 6.2. And there you go, Taylor. Thank you for identifying where that table was. This is what I was looking for. You can see that it gives you basic breakdown of each one of the types of reactions, and it gives you some like not like words, it gives you words to kind of describe what's going on. So if you start with two elements combining, you end up with a synthesis. One reactant only, decomposition. One element and a compound, single replacement. Two compounds, acid plus base, organic compound with oxygen. So a quick summary of everything that we did in that big long hour that we just sat through. So there you go, a nice easy way to be able to identify all of the types of reactions that are taking place there. So there you go, it goes up to Y. I want to jump into the next section so we can kind of cruise through this. We're actually going to encounter this again next week. This is the lesson that I'm going to go to KSS and do. I'm not sure when exactly we will end up at KSS, or I will end up at KSS, and I'm going to broadcast from KSS, but it'll be this lesson. So friend of mine, Mr. Wilkinson at KSS, he's a little bit behind where we're at. So this is where he is going to be next week. So we're going to jump into it now. You guys will be experts by the time you see it again. And what we're going to do is just a bunch of demonstrations based on some of the ideas and concepts we're going to discuss here. So rate of chemical reactions, this is unit 6.2. And really quick section, so we'll get it done in the next 30 minutes or so. And you guys will be ready to go. So reaction rate. Often, this statement's really true. Often controlling the rate of a chemical reaction is as important as having the reaction occur in the first place. Some reactions occur really quickly, and they can happen so fast that you can't even see what's going on. Some reactions can happen so slowly that it takes very long periods of time for the reaction to occur. And for us to observe it, that's not really helpful. So if we can control how fast or slow a reaction proceeds, we can kind of learn more from the reaction. So it is very important. Anyone think of why we would want a chemical reaction to take place really fast? What would be sort of an example of somewhere where you would hope a chemical reaction would go really quickly? Anyone think of any examples of that in your everyday life? And chemical reaction is really broad, right? There's literally billions of chemical reactions going on inside your body right now. Around you, there's chemical reactions happening everywhere. It's kind of like this big idea, right? But why would we want a chemical reaction to take place quickly? Or can anyone think of an example of something you would like to happen really quickly? Yes, in a science experiment, so we don't have to sit and wait for a long time. That's funny you should say that. When you make it to, if you make it to university chemistry, you do something called acid-base titrations, where you try to neutralize an acid and a base, and based on the volume you use, it tells you the concentration of the acid. Anyways, long story short, when you're doing the reaction, you have this long pipette, and you just open this little valve really slowly, and it just drips and drips and drips until the color of what you're dealing with changes. And when the color changes, you're done. So you can literally sit there pouring in the liquid really slowly, a drop at a time, and it can take forever, and then the color changes and you know how much you added, so then you're done. But if you go too fast, you get too much in there and the color changes and you don't know exactly when it changed because you just added a bunch at a time. So it was really frustrating. I had to do it like 3 or 4 times one lab, and that was an example where I wish the reaction would take place a lot more slowly. So why would we want a chemical reaction to take place quickly? An explosion is what Taylor said. And you might be thinking, well, we don't want explosions to happen in the first place, but there are lots of explosions that you want to happen all the time. When you're driving your car around, or your parents are driving you around, if the explosion of the gas in the cylinders happens really slowly, well, then your engine doesn't run properly. So that's a great example. This is what the textbook says. So to make a reaction happen quickly, these are the things you can do. And we'll look at all of these more in depth in a second. But for now, you can increase the temperature You could increase the concentration, you could increase the surface area, or you can add something called a catalyst or an inhibitor. So that's just a basic summary of what we're going to sort of discuss in the next few minutes. That being said, we talked about something happening quickly. We had the example of an explosion. Can anyone think of something in terms of a chemical reaction that you would want to take place slowly? Something that you encounter every day, possibly. What types of chemical reactions do we want to happen slowly? Is there anything in your life that is undergoing a chemical reaction, but you're like, oh no, I don't want that to happen. I wish it would happen slower. Maybe making sourdough bread. I don't know much about making sourdough bread. I assume it has something to do with producing some sort of gas with yeast or something like that to make it rise. If it happens quickly, do bad things happen? Maybe the bread will be really dense because you don't have those little air pockets in there. Is that kind of where we're going with that? Not much of a baker. I like that example. So to just generalize your example, Abby, maybe in cooking, you want things to cook really quickly. That's a chemical reaction. You're changing what's going on there. So cooking would be a good example. How do we prevent things from happening quickly? Slow rise is better using yeast because it's easier to digest. I was off, but that makes sense. Can you think of any other examples with food where we would want a chemical reaction to take place slowly? Does anybody have a refrigerator in their house? Anyone? Anyone at all? Why do we put food in the refrigerator? Why is it advantageous to keep food cold? Anyone ever think about why we do that? Pop. Like you don't want the carbon dioxide to escape too quickly. That's an example for sure. So why do we put food in the fridge? Why do we freeze food? Why does something like milk? Why do we put milk in the fridge? Anyone ever thought about why you have a fridge in your house? Slow down decomposition. Is decomposition a chemical reaction? Sure is. So it doesn't go bad. Perfect. That's a chemical reaction. Food going bad, food rotting is a chemical reaction. Vegetables are covered in bacteria. You put it in a fridge, the bacteria starts or doesn't break it down as quickly. So we put things in a fridge where it is cold to slow the reaction down. So a fridge is an example of something you use in your everyday life to slow a chemical reaction down. If you just leave food out, it goes bad in the presence of bacteria and all sorts of other things that are there. How about your car? I can always relate to cars. Does anybody have like a rusty old car that maybe your parents gave you or something like that? Rust on your car is an example of a chemical reaction. You have oxygen in the atmosphere. Your car is made of metal, which has a lot of iron in it, and the iron rusts. Iron oxide, that is what rust is. So I don't want my car to rust, so I wash it lots to keep the paint in good condition and protects the metal so it doesn't rust. That's the reaction I want to happen really slowly. So that's another example. So if you want a reaction to happen slowly, it's just the opposite of the things that you want to do to make a reaction happen quickly. So instead of increasing the temperature, you're going to decrease the temperature. Instead of increasing the concentration, you're going to decrease the concentration. If you were to increase the surface area, you would decrease it to slow it down. And if you were to remove a catalyst or add an inhibitor, that would also slow down your reaction. So here's two examples. Airbags in cars are kind of misunderstood. People often think that there's like a pressurized container of gas somewhere in your car that inflates the airbag, but it's actually a chemical reaction that's occurring. So you see behind me, One airbag is inflating on time, and the watermelon gets cushioned by the airbag. And then the other airbag is inflating 1/100th of a second too late. And that watermelon isn't having as good of a day as it did on the other side. So this is an example of why you would want a chemical reaction to happen very quickly. Airbags in your car. If the reaction takes place too late, all of a sudden your face is hitting the steering wheel, and then you have literally an explosion happening in your face. Not a good thing to happen. So we kind of take for granted these things sometimes. I bring it up. This is how airbags work. Basically, you have a sensor somewhere in your car, and it says, oh, you've been in a crash, so I should make a chemical reaction happen. You have something called sodium azide, which is something that produces nitrogen gas when it breaks down. It happens very quickly. In literally like 1,000th of a second, that airbag starts to inflate. So it's kind of incredible that it's not compressed gas that's inflating the airbag. It's actually a chemical reaction. The sodium azide is actually producing nitrogen gas. So yes, that's how your airbag works. A lot of people don't understand or know or care. Your brother had that happen to him. Hey, Taylor. Yeah, it's pretty common. Car manufacturers are now starting to realize that airbags are inflating really quickly, and that can do bad things to people. So they're trying to figure out ways to slow down the airbag inflation so they're not exploding into people's faces at the same time as providing protection still. So it's kind of a fine line. Do you want the airbag to be there? Yeah, you do, but you don't want it exploding when your face is really close to the steering wheel. And there's lots of examples of how that can happen in bad ways. And Taylor, you've just proved that. So temperature. Think about temperature. I forget what grade you talk about the kinetic molecular theory, but talk about adding energy to particles. They vibrate, right? So you have a solid, you can see beside me here, solid particles just are in this little lattice structure and they vibrate back and forth really quickly. If you add some energy, they speed up a little bit, then they turn into a liquid, and then you add more energy, they start going really fast, and they're a gas. And all sort of substances that we have will exist in solid, liquid, and gas form, depending on how much energy you give it. So if you want a reaction to speed up, if you increase the temperature, you're adding energy. You're making the molecules move faster. The faster they move, the more collisions they have. The more collisions, the more reaction that's going to occur. So if you want something to happen quickly, by adding energy, by speeding up the particles, by adding temperature. Remember, temperature is just an average of the energy of the particles in that substance. The more chances of bumps occurring, the more bumping you have, the more collisions you have, the more reaction is going to take place. So if you wanted to slow a reaction down, you could cool it down. You're taking energy out of the system. The reaction's happening slower because less collisions are taking place. So higher temperature, faster the reaction. Slower temperature, slower the reaction. And we get back to the idea of the fridge. If you are going to put food in your fridge, why does that help? Well, it slows everything down. Less collisions, less reactions, longer your food lasts. Cooking food, same idea. You add a bunch of heat to food, it cooks quickly, that kills the bacteria, produces new things that we like. You don't want that to happen over several days. Just making a meal would not be that fun. So that's temperature. That's what we can do to speed up a reaction. Concentration. Concentration talks about how many molecules there are in something. You can have a really high concentration. Now, the best example I can think of is making like iced tea or juice or something. So if you had a glass of water, and then you take your powdered iced tea mix and you put a tablespoon, or make hot chocolate or something like that. Put a tablespoon in, you stir it, and you take a sip, and you're like, that's not sweet enough. So you want to add more powder until it gets sweet enough. You're increasing the concentration, or adding more sugar essentially. So if you think about adding stuff, the solution becomes more concentrated the more you add. So if you were to add this little solid, it dissolves in the water and you end up with a solution. The more concentration, same idea. The more opportunity there is for collisions to happen. So if you want lots of collisions to happen, you have a lot of concentration, that's kind of what you're looking for. Or you can do the opposite. You can reduce the concentration. You can dilute it more. You can add more water, make it less sweet, and less collisions will occur. So you have a slower reaction happening as a result. So that's how concentration affects reaction rate. Surface area. The more surface area you have, the more opportunities for collisions to occur. So if you take if you imagine like a sugar cube is full of sugar, but if you were to put your sugar cube in your tea, the only place the tea is touching the sugar cube is on the 6 sides. You have 6 sides. Well, what if you took that sugar cube and you crushed it up into a powder, and now have you increased the surface area? Yeah. Now you have a lot more area to have sort of collisions occurring. So behind me here, we have one big cube, and then if you took that cube and you divided it into smaller pieces, now instead of having the 6 sides for this surface area, you still have the 6 sides, the top, the bottom, the left, front, back, but now you also have these additional surface areas in the middle, so you're adding more surface area. Now if you took these cubes and broke them down into 4, you still have the original surface area, the 6 original sides. You still have these sides from these cubes, but now you have a bunch of additional sides up these gaps in the middle. So by breaking a solid object down, you are increasing the surface area. And sometimes students have a difficult time wrapping their head around how taking a solid and completely crushing it into a powder increases the surface area. But it does. Just think about that one sugar cube, and then you cut it in half again. Now you have 4 smaller sugar cubes. So you still have the original area, but a bunch of additional area. You cut those smaller. You could keep doing that until you end up with just a really fine powder. And those tiny little sugar grains, you could reassemble back into one big sugar cube. And each one of those grains, you imagine, had 6 sides. You've increased the surface area a lot. The best example I can use to describe this is medication. I think it's a pretty good example. These red dots are showing sort of collisions occurring. If you have one solid object, all of these molecules in the middle here, they aren't taking part in any of collisions. Just the outside is taking place in collisions. So all of these are kind of hidden. You're limiting how much you have. But if you broke up the green into all of these smaller pieces, now you have all sorts of surface area. Now there's almost every single one of those molecules is now exposed to a collision. If you crushed your house into a powder, would it still increase surface area? I'm not sure I understand where you're coming from or going with that, but yes, I'm not sure. I'm kind of picking up what you're trying to get at there. The example I use in medication is this. If you get some medication that's long-lasting, say you have a cold, you go to the pharmacy and or you have a headache or something. Long-lasting pills come in these little tablets. Why? Because they have a very low surface area and your stomach kind of dissolves them over long periods of time. You're only going to have that outside sort of acting. If you want a fast-acting medication, they usually come in these little capsules. And when they get into your stomach dissolves the capsule outside and all the powder gets released and it acts really quickly. So long-lasting medications will be in these tablets. Fast-acting medications will almost always be in capsules. And inside the capsules, there'll be a fine powder because your body can absorb that much more quickly than it can here at eroding the outside surface, like one atom at a time sort of thing. So that's a a pretty good example of, at least in my opinion, on how you sort of encounter these sorts of ideas in everyday life. Surface area, put in a capsule is powder, dissolves. Gel, same idea, great example. So gels are liquids, and sometimes that's what we'll do. It kind of gets back to the idea of concentration. Liquid is even better. It can get dissolved even faster because it doesn't have to dissolve the solid into any liquids in your digestive tract. So I have these, I don't like taking pills, but I have, I think they're Advil cold and sinus. They have like a sugary coating on the outside, and I don't mind it. But some of them they do taste pretty bad. I guess you're an adult when you're taking, medications that don't taste good anymore. Not like when you're a kid and everything had to be covered in sugar to make it palatable. The last thing is called a catalyst, or an inhibitor is the opposite of a catalyst. Now, catalyst is a general term that we deal with in science. If you're talking about an organism, so anything that's living, so living systems don't use catalysts. They use the exact same thing, but we call them enzymes. So a catalyst and an enzyme are the same thing. If we're talking about your body, you're dealing with enzymes, or any animals, things like that. If you're talking about sort of chemical processes, you're talking about catalysts. So same thing, they do the exact same thing. And what they do is they help bonds form, or they rearrange molecules so they can combine together more quickly. Now, remember when I did the elephant's toothpaste demonstration? It was hydrogen peroxide, H2O2, and it broke down into water and oxygen gas. What did I do to make that happen really quickly? I added something called potassium iodide, and potassium iodide is just a catalyst. It didn't actually take part in the reaction. It wasn't H2O2 plus Ki produces these other things. So catalysts don't take part in the reaction. All they do is kind of arrange things so the reaction can happen more quickly. And an inhibitor is the exact same idea. It's just the opposite. It makes it really difficult for the reaction to occur if you want a reaction to happen more slowly. So the tricky thing here is it doesn't actually participate in the reaction. It is there, it's present. So I took the hydrogen peroxide, I dumped in the potassium iodide. It was there, they mixed together. But in terms of a chemical reaction, the potassium iodide didn't actually react. It just helped the reaction occur. And there's a really interesting picture here behind me about how enzymes work. So this is kind of a really simplified idea of how you can get an enzyme to work. So let's say you wanted these 4 things to react. So you had these 2 little yellow guys and these 2 red guys, and you wanted them to all combine together to produce this new thing here. Well, this is the enzyme. It basically has on its surface, or some other way, it has spots for these things to fit together. And when they fit together, they can combine, and then they produce this new thing. So you can see how the enzyme isn't actually part of the reaction. These are your reactants here, or catalysts are the same thing, right? These are your reactants, and this is how you want them to combine together. If they were just left to chance out here, they might not combine perfectly in this manner. Their backs might bump into each other and they wouldn't combine. Things like that could happen. But when you add an enzyme or a catalyst, it lines everything up. It makes those 2 reactants come together in a way that they're going to combine together. So the enzyme isn't actually taking part in the reaction, it's just there to help things move along. So that's how an enzyme or a catalyst works. The example we have here in the notes is salivary amylase, which is it's produced in your mouth. And when you're in grade 8, I think you talked about body systems, and you might have actually done this. And if you haven't, it's kind of interesting. If you take a piece of bread has really long carbohydrate chains. If you break down carbohydrates into smaller and smaller pieces, they turn into sugars. So if you were to take a piece of bread, without chewing it, you just put it in your mouth and you leave it there. When you initially put the bread in your mouth, it's not very sweet. But if you were to leave it for, several minutes, the salivary amylase that your mouth is producing, it starts to break down those really big carbohydrates into sugars. So the bread that's just sitting in your mouth will actually become sweet. So that's an example of what an enzyme does in your body. And you have, I don't even know how many thousands, if not hundreds of thousands of enzymes in your body that help reactions take place. That's just one that is pretty common. Another one you might have heard of if you're into cars, I'm always into cars, is catalytic converters. So we talk about a catalyst, catalytic, same idea. Basically all new cars that are made, if they're a gas-powered car, they have a catalytic converter in the exhaust. And it's kind of like a honeycomb structure on the inside. Your exhaust pipe goes through it. And basically what it does is it takes really nasty sort of chemicals that would normally get put into the environment, and it makes them into not as bad chemicals. So it is a part of a chemical reaction that changes the exhaust of your car into things like carbon dioxide, which aren't as bad for the environment. They're still bad, still carbon dioxide, but it changes them into less bad things. So almost all new cars, well, all new cars have it if they're gas powered. They'll have several catalytic converters full of really expensive metals like platinum and things like that, because platinum is a good catalyst when it comes to exhaust on your car. That's it, guys, for that section. It's not very long. So generally the questions in this particular section aren't really challenging as long as you can remember the things that will speed up or slow down reactions. So you have, if I jump back here, you have temperature, you have concentration, you have surface area, and you have catalysts and inhibitors. And just remember, surface area and concentration are really closely related. If we dissolve something in water, then we talk about concentration. If we're talking about just a solid, then we can be talking about surface area. Can you go back to concentration? Yes, I can go back to concentration. There you go. When would I like the learning guide for this to be done? I know we kind of started slowly and then we did that Unit 4 stuff for a long time. And I want that Unit 4 stuff done for tomorrow, I think I said. I said Tuesday or Wednesday this week, so if you get it in for tomorrow, that'd be great. If you can get this Unit 6 stuff done by Friday, or let's go with Monday. I'm not going to mark it over the weekend anyways. So if you can get Unit 6 in by Monday, we'll start Unit 5 on Thursday. So again, Unit 4 stuff, it's due tomorrow. If you can get it scanned and submitted online, perfect. If you want to drop it off, that's fine. Unit 6, which we just did right now in one day. Unit 6 will be due on Monday next week. That'll give you plenty of time. If you want to hand it in before then, that's perfect. If you want to bring them both in at the same time, like Abby is suggesting, that would be a good idea as well. And then we're going to start Unit 5, which is a little bit longer. And we'll spend probably all of the remainder of this week and next week on it. So that's Unit 5. And that's the end of chemistry. So chemistry is Units 4, 5, and 6. So we've done 4 and 6. We have 5. And then Unit 7 is actually on physics, but it kind of looks like chemistry. So some of you may think it's chemistry. We'll be talking about elements and things like that. Yeah, so great question, Anna. Can we go over the learning guide next day? Of course. If you guys have questions next day with respect to the learning guide, and I know the answers are there, Abby, which is great to check, but if you get something wrong, it's not going to tell you how. So I'll be happy to go through a bunch of the balancing questions or the balancing or the types of reaction stuff or speeding up or slowing down. Anything from the learning guide I can go through next day if you have questions, so don't think you have to have it done right away. And that's that. Does anybody have any questions before we take off for the day? That's Unit 6. Normally we'd probably go for another 20 minutes or so, but you guys have some time to go through the questions. And then we can just meet next day if you have anything that comes up, and we can go through that. Could you end us the notes of the midterm? Send us the notes of the midterm, like your solutions? Is that what you're asking for, Taylor? If you want me to scan your midterm for you and send it off, let me know, and I will do that. But you need to send me a message in Moodle, because if you all send me a message right now, I going to go to my office and I won't see it. So if you want me to send your midterm to you, perfect, thanks Taylor, and you want to go over anything off the midterm, I'd be happy to do that next day as well. So just send me a message in Moodle, and that way I'll know I can fire it off to you if you're interested, and then we can go over anything that might have come up. But if not, we'll end her there. So thanks very much, guys. Hope you guys have a great afternoon. A reminder that we have the Bumbershoot drama thing tomorrow. I don't have a whole lot of knowledge of what it's about, but it is from 12:15 to 2, and that's just right down by our building on Cannery Lane. It's like a drama acting company thing there. So if you're interested in that, that's tomorrow. And then we do have golf again on Friday. So just a heads up, and get out, enjoy the sunshine. We'll see you guys on Thursday. Thanks.